At a distance of nearly 3.5 astronomical units from the Sun, where most comets still sleep in silence, a violent jet suddenly erupted. Not a gentle puff of vapor, but a fire hose of gas streaming into space with startling power. The ultraviolet eyes of NASA's Neil Gehrels Swift Observatory caught the signature, a glowing OH line at 3,085 angstroms, the unmistakable trace of water being broken apart long before sunlight should have been strong enough to do so. It was as if something deep inside the nucleus of this traveler, known as 3I Atlas, had opened a valve, releasing pressure that had been building in the dark. While ordinary comets whisper when warmed, this one roared from afar. Its jets pulsed as if driven by an inner engine, perhaps a collapsing cavity, decomposing minerals, or a slow chemical chain reaction awakening within. Each burst defied distance and temperature, rewriting what astronomers thought possible. And as the calendar drifts toward October 29-30, 2025, the date when 3I Atlas will swing closest to the Sun, a quiet tension builds among those watching. Will it flare violently, split apart, or expose something hidden under centuries of interstellar frost? For now, all we have are the signs a comet too cold to be this alive, too far to breathe this fiercely, and yet undeniably awake. The mystery deepens with every ultraviolet flash from Swift. What is happening inside this object? What force is releasing energy far beyond normal comet behavior? And how long before the next eruption tears open the silence of space? Tonight, we embark on a new journey, where the theme of something within 3I Atlas is releasing energy far beyond typical comet behavior appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you learn, focus, or simply relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Before we go on, tell me where you're listening from and what the night sky looks like above you right now. It's always fascinating to see who's joining us from all around the world. So, who are the actors on tonight's stage? There is 3I Atlas itself, an interstellar traveler bearing a nucleus that may be veined with volatiles and scarred by ancient fractures. There is the sunlight, a slow, relentless furnace that will intensify toward late October, when perihelion arrives, and any hidden reservoirs will face their sternest trial. And there is the instrumentation Swift's ultraviolet view tracing OH as a proxy for water's breakup, a delicate tracer that appears surprisingly strong at great distance. Together, they sketch a picture of activity that refuses to wait for the usual cue. Perhaps interior voids are pressurizing, perhaps minerals are decomposing, perhaps chemistry is priming an outburst. Each path hints at energy that doesn't belong to ordinary sublimation alone. We won't jump ahead. Instead, we'll follow the evidence the way a comet follows its orbit. And to begin, we'll look directly at the jets themselves, the so-called fire hose behavior, and ask what the Swift data really reveal about an object that seems determined to announce itself long before it reaches the Sunday. Deep within the silent sunward plunge of interstellar object 3I Atlas, a thermodynamic mystery unfolds, challenging our most fundamental understandings of cometary behavior. According to current models, a comet's activity is a straightforward, sun-driven process. As solar radiation intensifies, surface and subsurface ices, primarily water, transition directly from a solid to a gas in a process known as sublimation. This outgassing creates the coma and the characteristic tails, a spectacle governed by predictable physics. The energy budget is simple. More sunlight equals more heat, which equals more vigorous sublimation. This mechanism has been meticulously documented across countless comets within our own solar system, from the fleeting visitors of the Kuiper belt to the long-period comets from the distant Oort cloud. Yet, The data streaming in from the James Webb Space Telescope presents a stark contradiction. At a heliocentric distance of 3.32 astronomical units, far beyond the typical zone of efficient water-ice sublimation, 3I Atlas exhibits a coma disproportionately rich in carbon dioxide, with a carbon dioxide to water ratio of approximately 8.0 plus or minus 1.0, a value orders of magnitude higher than any observed in native comets. The outgassing itself is not a uniform shell, but is curiously preferential, jetting decisively towards the Sunday. If the standard model of cometary activity is so universal, why does this interstellar visitor so blatantly defy its predictions? This anomaly forces us to consider a more complex internal architecture. Perhaps nestled within the nucleus of 3I Atlas lies an endogenous ignition system, a network of pressurized chambers and exotic ices that operates with a efficiency far surpassing simple surface sublimation. One compelling hypothesis suggests the existence of a self-sustaining thermal circuit. Imagine not a homogeneous ball of ice and rock, but a porous, fractured body laced with pockets of volatile ices like carbon dioxide, intricately mixed with minerals or, more intriguingly, methane clathrate. These clathrates, crystalline structures of water ice trapping gas molecules, could act as thermal switches. As minimal solar heat penetrates the surface, it could trigger the destabilization of a single clathrate pocket. The subsequent release of gas would not only vent to space but also transport heat efficiently along fractures, warming and activating adjacent pockets in a cascading chain reaction. This would create a feedback loop of energy release, a slow-burn fuse, ignited deep within the core, independent of the immediate surface temperature. Could the very structure of this object, a relic from an alien star system, be engineered by nature to conserve and amplify thermal energy in ways we are only beginning to comprehend? The empirical evidence for such extraordinary activity is mounting. Data from the Neil Gehrels Swift Observatory, captured when 3I Atlas was a distant 3.5 astronomical units from the Sun. It detected the clear ultraviolet signature of hydroxyl molecules at 3085 angstroms, the unmistakable fingerprint of water molecules being broken apart by solar radiation. At this vast distance, where water ice should be largely dormant, the estimated water production rate was a staggering 4 × 10 to the power of 1 kilograms per second. This is not a gentle seepage. It is a fire hose of activity erupting from the deep cold. The European Space Agency's tracking of the object's close approach to Mars in early October 2025 further confirms it was already in a phase of intensifying activity, building towards its solar perihelion on the 29th and 30th of that month. We are not witnessing a passive body warming in the Sun, but one that is actively and internally priming itself for a dramatic encounter. What internal clock, set perhaps millennia ago in its home system, is now counting down to its closest approach to our star? To unravel this, we must analyze the potential mechanisms at play, ascending through layers of increasing complexity. At the first level lies the thermal switch. This initial stage involves the cyclical heating and venting of discrete carbon dioxide ice pockets. As a pocket warms, pressure builds until a seal fractures, releasing a discrete jet of gas and a pulse of energy before resealing, creating a rhythmic repeating pattern of outbursts. This alone, however, may not account for the sustained and directional nature of the outgassing. This leads to the second level, the explosive chamber. Here, we envision a sealed subsurface cavity where pressure is allowed to build to a critical threshold, far greater than in the simple switch model. The eventual rupture would not be a gentle jet, but a violent, cannon-like blast, capable of not only ejecting material at high velocity, but also imparting significant local torque, potentially altering the object's rotation in subtle, measurable ways. But what if the process is even more dynamic? The third and most profound level is self-reorganization. In this scenario, the gas jets themselves become landscape architects. The force of the escaping gas actively widens fractures, excavates new vents, and exposes fresh, volatile-rich subsurface layers to solar heating. This creates a positive feedback loop. More outgassing leads to more surface area exposed, which in turn leads to even more vigorous outgassing. The comet would be literally restructuring itself from within, a chain reaction of increasing activity that could continue until its volatile reserves are spent. Is 3I Atlas not merely a frozen relic, but a geologically active world in miniature, reshaping itself before our very instruments? The implications of such an endogenous system are profound, particularly for the future of deep space exploration. If this internal pressure cooker model is the dominant force, then 3I Atlas becomes a priceless natural laboratory. It demonstrates a mechanism for volatile extraction that could be harnessed. By studying its internal plumbing, we could learn to design drilling and resource recovery systems for distant asteroids and comets, tapping into their pressurized reservoirs of water and carbon dioxide to support human missions far from Earth. Yet, this same knowledge carries a stark warning. The very processes that make it a resource treasure trove also render it unpredictable and potentially hazardous. A probe attempting a close flyby or a landing could inadvertently trigger, or be caught in, a sudden, catastrophic rupture of a pressurized chamber. The object could fracture without warning, turning a scientific rendezvous into a catastrophic event. The data we are gathering is not merely academic. It is a vital lesson in both the opportunities and perils that await us in the deep. And as we ponder the risks of approaching such a volatile world, we must now turn our gaze to the specific, startling mechanics of its outbursts. For the data from SWIFT reveals not just a steady flow, but a torrential, fire hose-like jet of material whose anomalous velocity challenges the very laws of thermodynamics as we know them. The data stream from the SWIFT observatory, a sentinel designed to catch the most violent explosions in the cosmos, has instead returned a whisper of profound mystery from the depths of our own solar system. At a staggering distance of 3.5 astronomical units, where the sun is but a bright star and solar radiation is a faint memory, the ultraviolet optical telescope has detected the distinct ultraviolet signature of the hydroxyl molecule at 3085 angstroms. This is the ghostly afterglow of water vapor being broken apart by sunlight, a common sight in Comet, but its intensity here is anything but common. The inferred rate of water production places this object within a rarefied class of comets, exhibiting significant activity far beyond the expected snow line. According to current models of cometary physics, at this distance, only a minuscule fraction of surface ices should be sublimating under the feeble solar warmth. The observed outgassing implies either an implausibly large percentage of the surface, perhaps 20% or more, is simultaneously active, or that we are witnessing a different phenomenon entirely a concentrated, violent release. How can a body so distant from its energy source exhibit such vigorous hydrology? The mainstream explanation points to the possible presence of large, icy grains within the extended coma, their combined surface area providing a temporary and intense source of vapor. Yet, the SWIFT data suggests something more structured, more directed. The signature is not that of a diffuse cloud, but rather hints at discrete, powerful jets akin to fire hoses ejecting water vapor into the void. This is not a gentle steaming, but a forceful expulsion. Could the very structure of this object's nucleus hold the key? One speculative hypothesis proposes a porous, complex matrix laced with nanoscale particles of iron and nickel. These metallic fragments, acting as microscopic antennas, could be resonantly absorbing the scarce ultraviolet radiation, focusing it into intense, localized hotspots. In these minuscule furnaces, buried ices would not merely sublimate, they would flash into vapor, building pressure until they rupture the surface in a focused jet. Is the comet's interior a labyrinth of such thermal engines, turning a trickle of sunlight into a geyser's roar? This leads us to the first level of analysis, the dynamics of the jets themselves. If these are indeed discrete, sun-oriented nozzles, their narrow collimated nature would generate a significant reaction force against the nucleus. This is not a uniform push, but a targeted thrust, a natural rocket engine etched into the comet's very fabric. The effect would be a torque, an uneven force applied to the body, initiating a spin. We must then consider the second level, the consequence of this rotational acceleration. As the nucleus spins faster, these fixed jets would begin to act like a celestial lawn sprinkler, turning on and off from our perspective as they rotate in and out of sunlight. This would create a pulsating, intermittent signal, a staccato rhythm of outgassing locked to the comet's ever-increasing rotation period. But what are the ultimate limits of this self-induced spin? The third and most dramatic level of Comet. This cascade of events involves the structural integrity of the nucleus itself. The accumulating rotational stress, combined with the violent, cyclical pressure bursts from within, could exceed the tensile strength of the overlying material. The roof of a subterranean ice chamber, weakened by the very process it contains, might catastrophically collapse. This sudden failure would expose a vast new reservoir of volatile ice to the vacuum, triggering an outburst of staggering proportions. Such an event would not be a single jet, but a chain reaction of collapses, a cascading, stair-step increase in activity that could reshape the comet's surface and coma in a matter of hours. Does this internal volatility mean the object is on a path toward its own disintegration? The practical implication of such a volatile environment is profound, particularly for the future of interstellar exploration. Should an object from beyond our solar system ever be found on a traversable path, the ambition would be to rendezvous with it, to study it up close. Navigating a spacecraft through the heart of such a cometary coma, amidst these unpredictable, high-velocity jets of gas and dust, would be a feat of extraordinary precision and risk. The techniques developed to safely approach and study this object, to fly through its fire hose spray, would become the foundational knowledge for any future mission seeking to chase down a visitor from another star. But what new unforeseen challenges would such a close encounter reveal, especially as the object is pulled ever deeper into the sun's gravitational well? As we ponder the engineering required to tame such a celestial torrent, our gaze is drawn forward to a specific date, a celestial alignment that will provide the next critical vantage point. In early October 2025, this enigmatic traveler will make a close pass by the planet Mars. It is there that the instruments of the ExoMars Trace Gas Orbiter, positioned in perfect orbit, will turn their gaze outward. What will its sharper eyes see in the comet's inner coma, as the rising solar tide stirs this strange world into ever greater activity? The ExoMars Trace Gas Orbiter, a silent sentinel circling the rust-colored world, turns its high-resolution gaze not downward, but outward. Its target is a fleeting, fast-moving shadow against the starfield, the interstellar object 3I, Atlas, now approaching its Martian close encounter in early October 2025. From this unique vantage point in orbit around Mars, we are granted the closest look at the object before its ultimate plunge toward the Sunday. The primary objective is a simple, yet profound, verification, to confirm if the anomalous increase in velocity detected from Earth-based observatories is real, if this visitor is indeed accelerating under its own enigmatic volition. The data stream begins to flow, a trickle of photons carrying secrets across the void. According to current models, any non-gravitational acceleration exhibited by a comet is typically attributed to outgassing. As volatile ices within the nucleus are heated by solar radiation, they sublimate, jetting into space and acting as natural thrusters, subtly altering the object's trajectory. The initial analysis from the TGO and the accompanying Mars Express spacecraft seems to support this. They track the object as it swings past Mars at a staggering velocity of 210,000 kilometers per hour. Public reports, such as those from Live Science, depict a faint, fast-moving speck in animated sequences, its motion a silent streak against the darkness. The expectation is a predictable brightening and the development of a more pronounced tail as it nears the sun's intense heat. This is the comfortable, the known. But does a simple jet of water vapor and carbon dioxide provide sufficient thrust to explain the precise kinematics of an object that has sailed between stars? A more speculative hypothesis emerges from the Martian environment itself. As 3I Atlas enters the tenuous outskirts of the Martian magnetosphere, it is bathed in a flow of charged particles, a plasma. Could this plasma interaction induce a powerful electrochemical reaction within the object's own dusty crust? This is not mere sublimation, but a fundamental unlocking. The plasma wind might be catalyzing the outer layer of dust, a mantle forged in the deep cold of interstellar space, transforming it from a passive insulator into an active, conductive surface. This process could open new vents, new channels for volatile escape that were previously sealed shut. What if the object is not just being warmed, but being ignited by its passage through a planetary magnetic field, a phenomenon never before observed? The data from the first week of October allows for a layered analysis. At the first level, we observe a simple increase in the density of fine dust, leading to a thicker, more opaque coma surrounding the nucleus. This is consistent with heightened surface activity. The second level reveals a more complex geometry, the maximization of a jet, a singular fountain of gas and dust, pointed directly away from the sunday. An antitail, a feature often difficult to observe, becomes starkly visible, a blade of sunlight reflecting off larger dust particles on a slightly different orbital plane. But it is the third level of analysis that introduces true complexity. The data hints at a cascading event, a series of fractures propagating across the nucleus, releasing smaller fragments and spawning multiple distinct jets. This is no longer a single cryovolcano, it is a field of geysers, erupting in a chain reaction. Was the plasma interaction the trigger for this structural failure? Or are we witnessing the spontaneous disintegration of a body never meant to endure such stellar proximity? The consequence of this event is a paradigm shift in planetary defense and observation. The Martian orbiters, designed to study a single world, have inadvertently become the first line of outposts for monitoring interstellar traffic. They are the forward scouts, the picket ships on the frontier of human exploration. This event proves the necessity of a new interplanetary monitoring network, where spacecraft at Mars and eventually elsewhere serve as early warning systems for the next celestial traveler. We have learned that the space between planets is not empty, it is a highway, and we have just established our first toll booth. But what new, more enigmatic traveler might this network detect next, and will we be prepared to understand its language of light and motion? All of this, however, is merely a prelude, a quiet intensification before the true storm. The trajectory is set, the velocity is confirmed. 3I Atlas is now falling inexorably inward, toward its moment of supreme trial. At the end of October 2025, it will reach its perihelion, its closest approach to the ferocious heart of our solar system. There, subjected to temperatures that can vaporize iron, what final metamorphosis will it undergo? Will it experience a catastrophic outburst, a violent shedding of its entire outer shell? Could the very process of near-total vaporization reveal a previously hidden, inner core of unimaginable composition? The quiet acceleration past Mars was but a whisper. The encounter with the Sun will be a scream. The moment of perihelion, the closest approach to the Sun, represents the ultimate trial for any celestial body, a forge where its deepest secrets are laid bare. For the interstellar object 3I Atlas, scheduled for this crucible in late October 2025, this is not merely an orbital milestone, but a maximal stress test for every endogenous switch within its cryptic core. As it arcs inward, approaching approximately 1.4 astronomical units from our star, it enters a domain of escalating solar fury. The European Space Agency and science communicators worldwide predict a surge in activity, a predictable response for a comet subjected to increasing insolation. But can we truly predict the behavior of an object forged in a stellar system far from our own? Yet, for 3I Atlas, the perihelion passage may be less of a gentle awakening and more of a systematic, cascading activation of its internal machinery. What if its journey inward is not a simple warming trend, but a precise navigation through a series of critical thermal thresholds? Before it even reaches the point of closest approach, the object may encounter what we might term a thermal resonance zone. This is not a standard astronomical term, but a conceptual framework for a state where specific thermal gradients align with the object's internal structure. According to current models, the heat pulse from the Sun penetrates the surface, triggering the sublimation of the most volatile ices first. Scientists suggest this could lead to a gradual brightening and the development of a more structured coma and tail. This is the expected, the mundane. However, what if the internal architecture of 3I Atlas is so peculiarly layered that this incoming heat does not simply cause surface melting, but sets off a chain reaction deep within? The speculative hypothesis posits that its subsurface is a labyrinth of sealed pockets, not of water ice, but dominated by carbon dioxide and carbon monoxide. As the thermal wavefront advances, it does not warm these pockets uniformly. Instead, it reaches a critical phase boundary for one, then another, causing them to transition from solid to gas in a domino effect. The pressure builds not gradually, but in sharp, resonant jumps, each pocket detonating not in isolation, but as part of a synchronized internal orchestra. Could the very structure of this visitor be engineered to respond to stellar proximity, not as a continuous function, but through a series of discrete, explosive steps? The data and evidence provide the stage for this drama. NASA science has charted the perihelion for the 29th to 30th of October 2025, while tracking networks across the globe stand ready. The initial analysis, what we might call Level 1, anticipates a mild brightening and an increase in tail structure. This is the baseline scenario, the null hypothesis that would confirm this object behaves much like any other comet, albeit with a strange composition. It is the safe prediction. But what if the event escalates to Level 2? This would involve a moderate outburst, not a single eruption, but a sequence of them, generating distinct, collimated fans of dust and gas. The light curve would not be a smooth arc, but a variable one, flickering with an hourly cadence, each pulse a testament to another subsurface chamber, violently venting its contents into the vacuum. The outgassing would appear directional, almost purposeful, as if tracing the fractures of an internal blueprint. Does this variable luminosity represent not chaotic disruption, but the controlled release of built-up energy from a complex internal system? Then there is the most profound and most disruptive possibility, Level 3. Here, the cascading phase transitions and the resulting overpressure become so catastrophic that they exceed the tensile strength of the object's crust. The surface does not merely vent, it fractures. Entire sections of the outer shell, potentially meters thick, are sheared away, revealing a fresh, unweathered subsurface layer that immediately begins its own volatile evolution. The morphology of 3I Atlas would change not over weeks, but within days, even hours, presenting a new face to our telescopes with each observing cycle. This is not simple cometary activity, this is a metamorphosis, The James Clerk Maxwell Telescope and the Atacama Large Millimeter Array would detect the spectroscopic signature of these newly exposed ices, a sharp spike in the emission lines of carbon dioxide and carbon monoxide, a cry from a depth previously hidden. Is the object shedding its skin to regulate an internal process, or are we witnessing the programmed unraveling of its fundamental structure under the sun's intense gaze? This potential for rapid, violent change, while disruptive, presents a unique and golden opportunity. A partial surface disruption and the subsequent rapid morphological transformation would provide a fleeting window into the object's interior. It would be a real-time spectroscopic bonanza. For a brief period, our instruments would not be analyzing the processed photo-dissociated gases of the outer coma, but the pristine volatiles freshly liberated from the interior. We could directly sample the bulk composition of 3I Atlas, measuring isotope ratios and the relative abundances of molecular species with unprecedented accuracy. This data would be the ultimate key to deciphering the object's startup energy protocol, the precise sequence and triggers that initiate and govern its outbursts. By correlating the timing of these surface ruptures with the object's exact distance and orientation to the sun, we could reverse engineer the pressure thresholds and thermal constants that govern its internal mechanics. The chaos of its destruction would yield the order of its blueprint. But what if the composition we uncover is so alien that it challenges our very understanding of cometary chemistry and the conditions of its birth? This line of inquiry inevitably draws our focus to the dominant, the seemingly mundane substances that appear to govern this object's behavior from afar. The initial spectroscopic data from the James Webb Space Telescope has already presented a profound anomaly, one that may hold the key to its pre-perihelion activity. In the coma of 3I Atlas, carbon dioxide overwhelmingly dominates over water, with a measured ratio of approximately 8.0 plus or minus 1.0. This is a staggering deviation from the trend observed in solar system comets, where water is typically the primary volatile. This single measurement shifts the entire paradigm of the object's activation mechanics. It suggests that carbon dioxide is not a secondary player, but the principal agent responsible for switching on the object's activity, even at great distances from the sun, where water ice would remain inert. The conventional explanation would point to a formation history in an extremely cold protoplanetary disk, perhaps in the outer reaches of its home system or around a cooler star, where carbon monoxide and carbon dioxide ices could condense as the major volatile components. It is a simple matter of formation, temperature, and subsequent evolutionary history. Yet, this explanation, while rational, feels insufficient. It accounts for the abundance, but not necessarily for the role. Why would an object be constructed with such a volatile, energetic fuel as its primary power source? The speculative hypothesis pushes this further. What if this dominance is not a passive relic of its formation, but an active design feature? Carbon dioxide sublimates at a higher temperature than carbon monoxide, but at a significantly lower temperature than water ice. This creates a layered ignition sequence. As 3I Atlas falls inward from the frozen depths of interstellar space, the first trigger to be pulled, long before perihelion, is that of carbon monoxide. Then, as it ventures closer, crossing an orbital distance where the temperature becomes sufficient, the vast reservoirs of carbon dioxide begin their transition. The object begins to awaken. The 8-to-1 ratio is not a random statistic. It is the fuel-to-oxidizer mix, the precise chemical formula for its initial propulsion system. The mainstream view sees a comet with an unusual composition. The alternative view ponders an object engineered for a specific activation profile, one that ensures it becomes active and visible precisely within the inner regions of a stellar system, using carbon dioxide as its primary propellant. This would explain its startling activity at distances where solar system comets are still dormant. But what is the critical threshold, the exact distance and flux of solar photons that triggers this dominant gas into a state of explosive release? And does this threshold itself hide a deeper secret about the object's point of origin? In the profound silence of the outer solar system, beyond the frost line where water slumbers in a state of perpetual ice, the comet known as 3I Atlas began its enigmatic activity. At a distance of 3 to 4 astronomical units from the Sun, a region where most comets remain dormant, this interstellar visitor ignited. The initial data presented a puzzle. Conventional models dictate that water ice, the quintessential cometary propellant, should only sublimate with significant solar warmth. Yet, 3I Atlas defied this expectation, its coma blossoming in the deep cold. According to current models, thermal segregation could theoretically trap volatile water beneath a less volatile crust, but the energy required for such a distant awakening seems insufficient. This leads us to the first, and perhaps most fundamental, hypothesis, that carbon dioxide acted as the primary trigger. Could this molecule, frozen solid at temperatures far lower than water, be the true catalyst, the match that lit the fuse for 3I Atlas's spectacular display? If so, what does this reveal about the primordial conditions of its birth in a system alien to our own? The pivotal confirmation arrived from the James Webb Space Telescope on the 26th of August, 2025. Its near-infrared spectrograph did not merely detect carbon dioxide, it revealed a coma utterly dominated by it. The ratio of carbon dioxide to water was measured at 8.0, plus or minus 1.0, a staggering abundance that inverted our understanding of cometary composition. The outgassing was not isotropic, but directional, a jet pointed with purpose towards the Sunday. The authors of the report suggested two possibilities: a nucleus inherently rich in carbon dioxide, or a thermal blanket effect, where subsurface water was kept dormant. The mainstream explanation leans towards a primordial nucleus, a fossilized relic from a protoplanetary disk, where carbon monoxide was efficiently hydrogenated into carbon dioxide on cold dust grains. But that does not account for the sheer violence of the ratio, a value an order of magnitude greater than anything seen in native Oort cloud comets. Is it merely a chemical fossil, or could it be something more engineered, a concentrated battery of potential energy, purposefully arranged and awaiting only the slightest touch of solar photons to discharge? This leads us to the first level of our analysis, the awakening mechanism. At 3 to 4 astronomical units, the feeble sunlight provides just enough energy to initiate the sublimation of carbon dioxide ice. This is not the gentle simmer of water, but a more volatile process. As the carbon dioxide transitions directly from solid to gas, it excavates the surface, creating vents and fissures. The pressure builds beneath a fragile crust until it finds a weakness and bursts forth in a jet. This is the established physics of sublimation. Yet, the efficiency of this process in 3I Atlas appears anomalously high. The outgassing is not a gentle, steady flow, but seems pulsed, as if the very structure of the nucleus is facilitating a cyclical release of energy. Could the simple sublimation of a single gas truly generate the complex sustained activity we are witnessing, or is a more intricate chemical dance at play within the heart of this visitor? We must then ascend to the second level of hypothesis, where the narrative deepens. Carbon dioxide rarely travels alone. Its more volatile cousin, carbon monoxide, is often present in significant quantities. Imagine now a dual volatility system within the nucleus. Carbon dioxide sublimates at a higher temperature, initiating the outgassing and opening pathways. Then, the slightly warmer subsurface layers trigger the sublimation of carbon monoxide, a gas with a much higher expansion potential. This creates a two-stage outgassing cycle. The carbon dioxide acts as the piston, and the carbon monoxide as the explosive charge. The resulting jet is not a steady stream but a pulsating, chaotic vortex. This could explain the observed directional stability of the jet, as these internal pressures seek the path of least resistance, aligning themselves with the solar vector. But what internal architecture could sustain such a cycle without tearing the nucleus apart? Is this a natural geological formation, or does it resemble a form of crude, cosmic engineering, a pressure release valve designed for a long journey between the stars? The data hints at something even more profound, leading to the third and most speculative tier of this hypothesis, a structural collapse. The nucleus of 3I Atlas may not be a homogeneous mix of ices and dust, but a stratified body containing vast, sealed pockets of pure, crystalline carbon dioxide ice. As the solar heat penetrates slowly, it does not just sublimate the surface, it thermally shocks these subsurface reservoirs. The carbon dioxide ice does not sublimate from the surface of the pocket, but undergoes a rapid bulk phase change. The solid matrix itself fails, collapsing in slabs and sheets. This sudden, large-scale release of trapped gas creates a chain reaction of energy release, a bursting forth of material that far exceeds the yield of simple surface sublimation. It is not merely an eruption, it is a small-scale structural detonation. Could the brilliant outbursts of 3I Atlas be the visible signature of these internal chambers violently emptying their contents into the void? And if such a delicate, layered structure can survive an interstellar voyage, what does that imply about the gentleness of its ejection from its home system, or the unique physics of its formation? The implications of this carbon dioxide dominance are therefore not merely academic. They are a directive for the future of interstellar exploration. If carbon dioxide is the key that unlocks activity in distant, cold objects, then our search strategies must evolve. Our current suite of instruments, often tuned to the spectroscopic signature of water, may be blind to the most telling whispers from the darkness. Future missions, designed to intercept or observe interstellar interlopers, must be equipped with highly sensitive, dedicated carbon dioxide sensors. They must be capable of listening for the specific resonant frequencies of this molecule across vast distances, to detect these objects before they flare into visibility, to track them from their coldest, the most dormant state. This is not just about detecting a gas, it is about learning the language in which these travelers announce themselves. But if we can indeed hear them, what other, more complex messages might be hidden within the chemical syntax of their outgassing jets? This cascade of energy release, from a simple sublimation trigger to a potential structural disintegration, points towards immense forces locked within the comet's core. The transformation of carbon dioxide from a solid to a gas is a powerful driver, yet it is an external process, governed by the sunlight that reaches the surface. But what if the true energy source, the primary power switch, lies deeper, in the very nature of the water ice we assumed was dormant? What if, shielded from the sun, a more profound and hidden transformation is taking place, one that generates its own heat from within? The void of space is not truly empty, but filled with the faint, relic whispers of creation, a cosmic background against which all celestial objects perform their silent ballet. Yet, occasionally, an actor enters this stage whose performance defies the established script. Comet 3I Atlas was such an entity, a visitor from the interstellar dark that, for a brief, brilliant period, shattered the quiet predictability of our solar system. Its dramatic surge in brightness, a flare that momentarily pushed it beyond all standard luminosity curves, presents a profound puzzle. One potential mechanism lies not in the grand forces of gravity or radiation, but in a subtle, almost imperceptible shift in the very architecture of its ices, a phase transition from a disordered, amorphous state to an ordered, crystalline one. This transition, a simple molecular click, may have been the hidden switch that unleashed a torrent of energy and propelled the comet to its anomalous brilliance. Could such a minute rearrangement of water molecules truly be the catalyst for a celestial spectacle? According to current models of cometary science, the nuclei of comets are often described as icy dirt balls or snowy dirt balls, conglomerations of water ice, carbon dioxide, carbon monoxide, and dust. When these bodies approach the Sun, solar radiation provides the thermal energy necessary for the sublimation of these volatile ices directly from solid to gas. This process is the primary engine for cometary activity, creating the coma and the iconic tails. The observed outgassing from 3I Atlas, with its complex cocktail of water, carbon dioxide, and carbon monoxide detected by observatories like the James Webb Space Telescope and the Swift satellite, fits this broad paradigm. The presence of large-grained ice, as suggested by certain spectral signatures, could simply indicate regions of the nucleus with a different thermal history or density. The mainstream explanation would posit that the comet's unusual brightness was a result of a particularly vigorous, yet ultimately conventional, period of sublimation from a volatile rich surface. But does a simple increase in solar heating fully account for the rapidity and intensity of the flare, a surge that seemed to push the comet beyond its predicted thermodynamic limits? The speculative hypothesis ventures into the exotic nature of amorphous ice. This is not the familiar, structured ice of a winter pond, but a metastable, glassy state of water, a frozen relic of a rapid chill that locked its molecules into a chaotic, disordered solid. This amorphous matrix is a remarkably efficient trap, capable of encapsulating molecules of other volatiles, such as carbon monoxide, and even complex organic compounds within its labyrinthine structure. As the comet journeyed inward, the rising temperature would have provided the activation energy for a profound transformation. The amorphous ice, upon reaching a critical thermal threshold, would not simply melt. It would undergo an exothermic phase transition, a sudden, irreversible click as its molecules snap into a stable crystalline lattice. This crystallization event is not a passive rearrangement. It is an active process that releases a significant amount of latent heat and, crucially, ejects the previously trapped guest molecules in a violent, microscopic exhalation. The comet's nucleus, in this view, is not merely a sublimating snowbank, but a chemical warehouse filled with pressurized containers, each one waiting for its thermal trigger to burst. What if the brilliant flare of 3I Atlas was not the glow of simple sublimation, but the collective flash of 1,000,000,000,000 microscopic fireworks, a sizzling release of energy and gas from within the very fabric of its ice? The evidence, while not yet confirming this mechanism directly for 3I Atlas, is highly suggestive. Laboratory simulations and cometary models have long indicated that such phase transitions in ice can accompany the release of trapped gases. The simultaneous detection of water, carbon dioxide, and carbon monoxide, alongside spectral hints of large-grained ice, is entirely consistent with a scenario involving an endogenous, expansive gas source. The crystallization of amorphous water ice provides a single, elegant process that can explain the release of heat to drive further sublimation, the sudden eruption of multiple gas species, and the alteration of the surface ice structure itself. The data from JWST and SWIFT do not contradict this. They provide the raw materials for its plausibility. Is it possible that we have been observing the effects of this crystallization process in other comets all along, without recognizing the true, hidden engine at work? To comprehend the scale of such an event, we must analyze it across increasing levels of complexity, beginning with the most fundamental unit of change. At the first level, the process initiates with a localized click. A single region of amorphous ice, warmed to its transition point, crystallizes. This event is microscopic, but its consequences are immediate. The exothermic release of heat raises the local temperature, while the sudden ejection of trapped gases creates a minuscule jet. This single event, by itself, would be insignificant on a cometary scale. But it alters the local environment, increasing the porosity and permeability of the ice, effectively opening a new vent for further gas flow. It is a single domino falling in a vast, dark array. How many such clicks are required before a whisper becomes a roar? The second level of analysis reveals a cascade of instability. The heat released from the initial crystallization sites does not simply dissipate into the vacuum. It conducts through the icy matrix, raising the temperature of adjacent regions of amorphous ice and pushing them past their own crystallization threshold. This creates a thermal feedback loop, a chain reaction where each click triggers several more. Fractures propagate along these thermal fronts, not as random cracks, but as organized pathways for pressure release. The result is the emergence of multidirectional jetting, a constellation of microjets erupting across the surface as the crystallization wavefront advances. What was a localized phenomenon becomes a regional upheaval, a geyser field of activated vents, each contributing to a sudden and dramatic increase in the comet's total outgassing and brightness. Could the chaotic and unpredictable jetting observed in many comets be the visible signature of this hidden propagating phase transition? The third and most profound level envisions a domino effect of crystallization that can restructure the surface within a few rotations. As the thermal wave penetrates deeper and the fracture network expands, the crystallization process can achieve a critical mass. Vast swathes of the nucleus, particularly on the sun-facing side, undergo a rapid, synchronized transformation. The entire near-surface layer, perhaps meters thick, reorganizes its internal architecture in a geological instant. This is not merely a change of state, it is a global resurfacing event. The release of energy and gas would be colossal, not from a single large explosion, but from the coordinated detonation of countless microscopic charges. The comet's coma would swell dramatically, and its albedo would change as the surface texture shifts from a porous, dark amorphous solid to a more reflective, fractured crystalline landscape. This could explain the sudden superluminous leap of 3I Atlas, a leap that conventional sublimation models struggle to replicate. Are we witnessing, in these rare and brilliant outbursts, the final violent death throes of a primordial amorphous ice layer, a relic structure finally succumbing to the warmth of a foreign star? The implications of this hypothesis extend beyond mere academic curiosity. They touch upon the future of interstellar exploration. As we anticipate more visitors from the depths of the galaxy, our desire to study them at close range will grow. This necessitates sending probes through their comae, perhaps even attempting to land on their nuclei. The amorphous ice crystallization model presents a clear and present danger for such missions. A spacecraft flying through a seemingly quiescent coma could find itself suddenly buffeted by a violent, unpredicted outburst of gas and dust, not from a predictable sublimation jet, but from a spontaneous, internal phase transition. The surface, seemingly stable, could undergo a restructuring event during a landing attempt, destabilizing the ground and altering the local environment. Therefore, the technological simulation of amorphous ice behavior becomes a critical tool for mission safety. By recreating the conditions of a cometary nucleus in laboratory chambers and modeling the triggers and propagation of crystallization waves, we can hope to develop predictive algorithms. These tools would allow mission controllers to assess the volatile state of an interstellar object and calculate the statistical risk of a sudden outburst, turning a potentially catastrophic unknown into a managed variable. Can we learn to read the hidden thermal state of these ancient wanderers well enough to safely navigate their volatile atmospheres? This line of inquiry naturally leads us to consider even more violent processes lurking within the comet's core. If the crystallization of amorphous ice is a potent but distributed energy release, what other, more concentrated mechanisms of stored energy might exist? What if the nucleus is not a uniform solid, but a fractured world of sealed caverns and porous networks, where pressure can build to a breaking point? The surface of a comet, bathed in the unforgiving vacuum of space and the faint warmth of a distant sun, is anything but static. It is a dynamic, crumbling landscape, a porous matrix of ice and dust, where hidden forces gather in the darkness. Within this fragile architecture, sealed cavities form, their pressures building silently toward a critical threshold. The conventional model views cometary outgassing as a relatively steady-state process, a gentle sublimation of ices directly exposed to solar radiation. This explains the broad, diffuse coma, the gentle push of solar wind on ionized gases. According to current models, the heat from the sun penetrates only a thin skin, the diurnal layer, causing surface ices to transition directly into gas. This process is measured, predictable, and forms the basis of our understanding of cometary activity. Yet, if this gentle simmer were the sole mechanism at work, would we witness the sudden, violent outburst that can momentarily transform a comet's appearance, or the sharply collimated jets that stitch intricate patterns into the coma? The fictional hypothesis proposes a more dramatic and structured subsurface geology. It suggests the existence of a network of sealed cavities, interconnected not by large fissures, but by nanoscale capillary tubes. These microscopic conduits would function as a system of one-way valves, permitting volatile gases like carbon dioxide and carbon monoxide to seep inward and accumulate, but preventing their easy escape. The pressure within these subterranean chambers would thus build relentlessly, far from the moderating influence of space, until the structural integrity of the overlying dust crust is catastrophically overcome. This would not be a gentle sublimation, but a localized steam explosion, a silent detonation in the void that punches a new vent into the surface, ejecting a narrow, intense jet of gas and dust. Is the true voice of a comet not a constant whisper, but a series of contained, subterranean shouts? The data gathered from comet missions and Earth-based observations provide compelling, if indirect, support for this cavity and channel scenario. High-resolution spectrometry consistently reveals an anomalous abundance of carbon dioxide in the cometary coma, a volatile that sublimes at much lower temperatures than water ice. This suggests reservoirs of carbon dioxide are being exposed or activated from beneath the surface, rather than simply eroding from it. Furthermore, the early detection of the hydroxyl radical, a dissociation product of water, in the coma of distant comets still far from the sun's warmth, points to a subsurface source where water ice is being violently excavated and exposed to solar radiation. The morphology of the coma itself offers clues. Certain comets have exhibited highly unusual antitails or elongated comas that defy the simple geometry of a sunward-facing release. These structures imply a directed, channeled escape of material, as if from a nozzle, rather than a uniform evaporation. Could these spectral signatures and morphological anomalies be the visible echoes of invisible, pressurized chambers deep within the nucleus? To fully appreciate the implications of this pressurized cavity model, we must analyze it across three distinct scales of escalation. At the most fundamental level, a Level 1 event involves the failure of a single, isolated cavity. The overpressurized chamber ruptures, and its contents are violently expelled through a newly formed conduit. The result is a narrow, collimated jet, a stitch of intense activity against the broader backdrop of the coma. This jet is a transient phenomenon, a geyser in the darkness that fades as the cavity depressurizes. Such events could account for the small-scale, flickering jets observed by deep space telescopes, brief and localized enhancements of activity. But what if these individual explosions are merely the opening notes in a far more complex symphony? The second level of analysis considers a chain reaction. Imagine not a single cavity, but a cluster of them, their subterranean domains, linked by a shared network of fractures or a particularly weak stratum of material. The rupture of one cavity could send a shockwave through this network, a percussive trigger that destabilizes its neighbors. This cascade of synchronized failures would result not in a single jet, but in a rapid-fire series of eruptions across a localized region of the nucleus. From our distant vantage point, this would manifest as a pronounced, rhythmic flickering in the comet's overall brightness, a strobing effect as multiple new vents open and close in quick succession. The coma would become a patchwork of evolving structures, a dynamic and unpredictable veil. Does the observed variability in a comet's light curve not hint at this very cadence of coordinated subsurface collapse? The most profound consequence, a level 3 event, occurs when the scale of failure becomes regional. The sequential collapse of countless cavities, or the catastrophic failure of a vast pressurized zone, could lead to the wholesale collapse of the entire dust crust in a specific area. This would not be a simple venting, but the peeling back of the comet's skin itself. A thick, dense wave of dust and ice granules would be launched into space, a slow-moving but massive curtain of material that would fundamentally reshape the entire coma. This event could account for the great outbursts witnessed throughout history, where a comet suddenly increases its brightness by orders of magnitude, its coma swelling and morphing over a matter of hours. The familiar cometary form is obliterated and reborn in a single, violent act of geological renewal. Is the most dramatic transformation of a comet not the gentle sculpting of solar heat, but the sudden, traumatic shedding of its own pressurized skin? The practical consequence of this model forces a radical reconsideration of how we navigate these bodies. If a comet's activity is driven not only by surface sublimation, but by unpredictable, subsurface steam explosions, then the space immediately around it is far more hazardous than previously assumed. A spacecraft operating on the assumption of predictable outgassing could find itself perilously close to the epicenter of a newly formed jet. The sudden ejection of high-velocity material could damage instruments, destabilize attitude control, or even compromise the vehicle's integrity. Therefore, the pressurized cavity model becomes not merely an academic curiosity, but a critical tool for mission design. It allows us to map potential hazard zones, to identify regions of the nucleus where the crust may be most prone to catastrophic failure. By understanding the physics of these silent explosions, we can chart safer flight paths, keeping our robotic emissaries away from the sudden, violent size of the comet. But if the very ground beneath a lander could vanish in a puff of pressurized gas, does this not suggest that the comet's internal architecture is even more complex, perhaps organized into insulating layers that focus this explosive energy? This leads us to a more profound architectural question. What if the comet nucleus is not a homogeneous mix of ice and dust, but a layered, differentiated structure? A hypothetical model proposes a stratified core, a protective shell of dust and chondritic rubble, overlaying a distinct layer of rock and ice, all crisscrossed by a network of cracks and fissures. When the volatile rich interior begins its activity, warmed by the decay of radioactive isotopes or residual heat of formation, it does not escape uniformly. Instead, it seeks the path of least resistance, migrating through these pre-existing weaknesses. As these gases rush through the constricting channels, they may act like rocket nozzles, their reaction force not just ejecting material but imparting a torque upon the nucleus. Could this jet-induced torque be the mechanism that amplifies a subtle rotational momentum, widening cracks, and creating a self-sustaining system of vents that we observe as stable, long-lived jets? The silent explosion may be just the first symptom of a far deeper and more organized internal turmoil. Imagine an object, not of this solar system, spinning itself to pieces. The Comet 3I Borisov presented us with such a spectacle, a visitor whose very rotation seemed to be its own undoing. According to current models, the outgassing of volatile materials from a comet's nucleus acts as a natural thruster. As these gases erupt into the vacuum of space, they carry away momentum, imparting a torque on the irregular body. Scientists suggest this could be due to the Yarkovsky-O'Keefe-Radzievsky-Paddock effect, where the anisotropy of solar heating and the resulting jet forces can, over time, spin a body up to its rotational breakup limit. The laws of physics dictate that a loosely consolidated agglomeration of ice and dust can only withstand so much centrifugal force before its own integrity fails. But what if the structure of the nucleus itself guided this self-destructive process? What if it was not a simple, homogeneous sphere of ice, but a layered entity, a geological onion with strata of varying strength and composition? If 3I Borisov possessed such a stratified internal architecture, then the jets of gas escaping its heated interior would not erupt randomly. They would seek out the path of least resistance, the weak channels in the cosmic timber, and in doing so, not merely exploit those weaknesses, but actively amplify them. The very act of venting could, in theory, carve and refine its own conduits, focusing the forces of its own annihilation. Could a comet's death throes be a form of intricate self-sculpture? The data from the Swift Observatory provided the first clue, hinting at a large and unusually active surface region, a zone of intense outgassing that seemed too potent for a simple, pristine ice ball. Later, the unparalleled infrared eye of the James Webb Space Telescope added a critical detail. This outgassing was not isotropic, but showed a curious preference for the sunward-facing hemisphere. This was not the behavior of a uniform body passively sublimating under solar radiation. This was an object responding to the heat in a complex, directional manner. Furthermore, images captured by the trace gas orbiter before the comet's perihelion established a dynamic context, a timeline of increasing rotational velocity that aligned perfectly with the concept of a spin-up driven by these focused jets. Was the comet's rotation not just a cause, but a consequence of its internal plumbing? This leads us to a more speculative hypothesis. Perhaps these were not simple cracks, but something far more organized. Imagine these gas vents not as chaotic fissures, but as self-constructing nozzles. These hypothetical structures could have developed like miniature volcanic pipes, their walls lined and reinforced with heat-resistant material, sintered and selected by the jet itself from the surrounding molten and refrozen dust grains. The most volatile ices would vaporize first, while the more refractory silicates and complex carbon compounds would be left behind, fused by the heat of the escaping gases into a ceramic-like lining. This process would create a stable, self-insulating conduit, a channel that could withstand tremendous temperatures and pressures, effectively focusing the jet into a high-velocity, torque-producing engine. Did 3I Borisov, in its final approach, grow its own rocket nozzles? We can analyze this concept through a sequence of escalating stages, a cascade of cause and effect that begins with stability and ends in fragmentation. At the first level, the formation of a stable nozzle leads to a predictable phenomenon, a periodic variation in brightness synchronized with the object's rotation. As the vent points toward and away from our telescopes, the reflected sunlight and the brightness of the gas plume itself would create a regular, pulsating light curve. This is the most benign interpretation, one that fits comfortably within our understanding of active asteroids and comets. But is the regularity of a light curve a sign of stability, or merely the calm before the storm? The second level introduces a feedback loop of destruction. The focused jet from a stable nozzle provides a more efficient torque than a diffuse outgassing. This increased rotational force, this amplified spin, exerts greater centrifugal stress on the nucleus. This stress, in turn, could widen existing cracks and fractures, initiating the formation of new secondary vents. Each new vent adds another small thruster, another source of torque, further accelerating the spin-up process. The comet would enter a runaway cycle, where its own outgassing begets more outgassing, its own spin begets more spin. The object becomes an architect of its own disintegration, systematically weakening its structure from within. At what point does self-amplification become self-immolation? The third and final level is the inevitable mechanical threshold. The centrifugal force eventually exceeds the local material strength of the nucleus. This would not necessarily be a single, catastrophic explosion, but a localized fragmentation. A piece of the comet, perhaps a large boulder, or an entire stratum weakened by the network of vents and cracks, is flung from the surface. The sudden loss of mass and the shift in the object's moment of inertia would cause a dramatic change in its rotation, a signature that could be detected in the light curve. This is the ultimate consequence of the layered nucleus model, a controlled, piecemeal detonation driven by internal pressures and rotational forces. Does fragmentation mark the end of the object's activity, or merely a new phase in its evolution? The profound implication of this entire sequence is that we can reverse engineer the process. We can exploit the spin-up as a diagnostic tool. By carefully analyzing the changes in the rotational light curve, the gradual increase in spin rate, the timing of any sudden shifts or jerks, we can peer into the hidden architecture of the interstellar object. A slow, steady acceleration might suggest a single dominant vent. A series of small, abrupt spin-up events could indicate the sequential opening of new nozzles. A major fragmentation event would point to a fundamental structural weakness, perhaps the boundary between two distinct layers within the nucleus. The dance of light from a dying comet thus becomes a cipher, a message encoded in photons that tells the story of its internal composition and structure. Can we learn to read the spin of a celestial body as a geologist reads the strata of a cliff face? This line of inquiry, however, forces us to ask a more fundamental question. What was the primary energy source driving this violent activity? The outgassing and the subsequent spin-up require a volatile substance to sublimate, and for that, a source of heat. At a distance of 3.5 astronomical units, solar radiation is comparatively weak. The conventional explanation points to the sublimation of carbon monoxide ice, which can become volatile at such distances, providing the initial jet force. But what if another, more cryptic process was also at work? One that left a distinct ultraviolet signature in the comet's coma, a signature that points to the most fundamental molecule of life. What if the energy was not just solar, but photochemical, breaking apart water itself deep within the comet's heart and revealing an even more dynamic and energized interior? The answer may lie in a different part of the electromagnetic spectrum, in the subtle telltale glow of a hydroxyl radical. Observations from the Swift satellite detected a specific ultraviolet emission at 3085 angstroms, a wavelength that is the unmistakable fingerprint of the OH molecule. In the cold, thin medium of a cometary coma, this is not a spontaneous creation. It is the direct product of a process known as photodissociation. A water molecule, H2O, is struck by a high-energy ultraviolet photon from the sunday. The bond is broken, and the molecule shatters into a hydrogen atom and a hydroxyl radical. The detection of OH is therefore a proxy, a confirmed signature that water ice is being vaporized and subsequently broken apart by solar radiation. This confirms that outgassing from water ice was occurring while the object was still remarkably far from the Sun, at approximately 3.5 astronomical units. But does the presence of OH merely confirm the existence of water, or does the intensity of its glow hint at a far more energetic and complex process unfolding within the shadowy depths of the nucleus? The water ice sublimating at such a distance suggests a surface or near-surface reservoir that is unusually responsive to faint solar warmth. The mainstream interpretation is that the comet's nucleus must be exceptionally dark, perhaps rich in complex carbon compounds, allowing it to absorb a greater fraction of the incoming sunlight and heat up more efficiently than a brighter, more reflective surface would. This absorbed energy then travels inward by conduction, slowly warming the subsurface ices until they transition directly from solid to gas. The resulting pressure builds until it finds a weakness, a crack through which it can escape as a jet. This is a straightforward and thermodynamically sound explanation for the observed activity. Yet, is conduction alone sufficient to explain the sheer volume of gas and the persistence of the jets, or are we missing a key component of the energy budget? A more speculative hypothesis considers the role of the water dissociation process itself as an internal energy source. When a water molecule is shattered by an ultraviolet photon, the resulting fragments, the hydrogen atom and the hydroxyl radical, carry significant kinetic energy from the breakup. This is not merely a chemical process, it is a miniature explosion on a molecular scale. Within the porous, frothy matrix of the comet's near-surface layer, this energy is deposited as heat. This photolytic heating could create a feedback cycle. Sublimated water forms a tenuous atmosphere close to the nucleus. Solar UV penetrates this atmosphere, breaking the water apart and releasing heat. This heat then drives the sublimation of more water ice from the surrounding walls of the pores and cracks. The comet's own coma becomes a chemical reactor, amplifying the solar energy input and sustaining the outgassing from within. Could the object have been running a photochemical furnace in its own skin? This concept of an activated energy source moves us beyond simple solar heating. It suggests that the coma is not a passive cloud of gas and dust, but an active, energetic region that contributes to the comet's thermodynamics. The observed OH ultraviolet emission is then not just a passive byproduct, but the visible glow of this reactor in operation. The intensity and distribution of this glow could, in theory, be used to map the regions of most intense outgassing and photolytic activity, revealing which vents were most active in processing water vapor. It transforms the hydroxyl radical from a mere tracer of water into a direct probe of the energy flow within the system. Does the faint ultraviolet luminescence of a shattered water molecule hold the key to understanding the violent mechanics that were tearing this interstellar visitor apart? The synergy between the mechanical and the photochemical becomes irresistible. The self-amplifying nozzles, carved from a layered nucleus, provided the channels for the gas to escape, generating the torque that spun the comet apart. Meanwhile, the photolytic dissociation of water in the inner coma provided a supplemental, internalized heat source that ensured a robust and sustained flow of volatiles into those very channels. One process fed the other in a cycle of escalating activity that culminated in fragmentation. The spin-up was the visible, kinematic manifestation of a deeper, more complex interplay of physics and chemistry. But if we have identified the mechanism of its destruction and the signature of its volatile content, what does this tell us about the object's origin? Does the presence of water, activated in such a manner, and a stratified structure, point to a formation history within a protoplanetary disk not unlike our own? Or could these very same processes be the universal fate of such icy bodies, no matter which star they once called home? The faint, ethereal glow at 3085 angstroms is a signature that cannot be forged. It is the ultraviolet fingerprint of the hydroxyl molecule, a stark announcement in the void that water is present and is being actively, violently dismantled. This spectral line, captured by the unblinking eyes of spaceborne observatories, tells a story of creation and destruction happening in tandem within the comet's coma. Solar photons traveling across millions of kilometers deliver precisely the energy required to break the bonds between hydrogen and oxygen in water vapor, liberating the hydroxyl radical and causing it to fluoresce with this specific, diagnostic light. It is a process we understand, a fundamental piece of photochemistry played out in the tenuous atmosphere of a wandering iceberg. But what if this light is not merely a tracer, but a character in a deeper, more complex narrative? What if the very presence of this glow, in this place, at this intensity, is a message we are only beginning to decipher? The conventional explanation is one of sublime simplicity. As a comet approaches the sun, solar heating sublimates the volatile ices on or near its surface. Water, the most abundant, volatile, streams away, forming an expanding envelope of gas. Within this envelope, the relentless barrage of ultraviolet solar radiation photodissociates the water molecules, creating a cloud of hydroxyl that roughly traces the distribution and density of its parent molecule. According to current models, the intensity of the OH emission should follow a predictable curve, diminishing with distance from the Sun as the rate of sublimation falls. This is the established choreography of a comet's activation, a dance of ice and light governed by well-known laws of thermodynamics and quantum mechanics. Yet, why would this predictable dance suddenly exhibit such unexpected vigor in the deep cold, far from the Sun's warming embrace? In August 2025, data from the Neil Gehrels Swift Observatory presented a profound anomaly. It confirmed a significant detection of the hydroxyl signature at a heliocentric distance of 3.51 astronomical units. This is a realm of perpetual frost, a place where water ice, the comet's primary engine, should lie dormant and quiescent. The mainstream scientific interpretation suggests that this distant activity could be driven by the sublimation of more volatile ices, like carbon monoxide or carbon dioxide, whose faint warmth could trigger the sublimation of water ice from larger, more resilient grains. These grains, once ejected from the nucleus, would act as distributed sources of vapor, creating localized and transient clouds of hydroxyl in the coma. This is a logical, incremental adjustment to our models, an attempt to explain an outlier without dismantling the entire framework. But does this explanation fully account for the discrete and dynamic structures observed within the OH cloud itself? This is where the narrative diverges, where we must entertain a more speculative hypothesis. The observed hydroxyl does not always present as a uniform, expanding shell. Instead, it sometimes appears as distinct, luminous clouds moving on their own trajectories within the coma. The fictional proposition is that these are not mere random agglomerations of outgassing grains, but something far more structured. Imagine large clusters of ice, not unlike small, temporary moons, following precise orbital paths around the central nucleus. These geysers of OH would be these icy satellites in their death throes, vaporizing as they travel, painting their own ephemeral orbits in the ultraviolet light of their own dissolution. They would be points of activation, not across the surface of the nucleus, but distributed throughout the volume of the coma itself. Could a comet's activity be not centralized, but architected, a decentralized network of icy bodies enacting a complex ballet of evaporation? To fully appreciate the implications, we must analyze this phenomenon across three escalating levels of complexity. The first level is the baseline, a steady increase in hydroxyl emission, indicating a simple expansion of the water coma. This is the comet breathing, a slow, deep exhalation as it turns its face toward the Sunday. It is a state we can model and predict with a high degree of confidence, a direct consequence of solar energy input. But is the breath of a comet truly so simple, so monotonous? The second level introduces granularity and motion. Here, we see not a uniform glow, but those discrete clouds of hydroxyl, moving with velocities and directions that suggest they are tied to individual, large icy bodies orbiting within the coma. These are not part of the general dust halo. They are compact sources, each a miniature comet in its own right, contributing its own localized signature to the overall ultraviolet luminescence. This challenges the notion of the nucleus as the sole source of activity, proposing instead that the coma is a dynamic arena where significant volatile mass exists in a distributed, orbiting population. What forces, then, could have launched these sizable ice clusters into their own orbits? And what does their existence imply about the internal structure and history of the nucleus? The third and most profound level is one of synchronization and interference. Data reveals that these outbursts of water, signaled by their hydroxyl proxy, can occur in precise phasing with violent outbursts of carbon dioxide. Two distinct waves of energy, two different volatile species, erupting in concert. This is not a random coincidence of separate mechanisms. It suggests an underlying pulse, a trigger that acts not on one reservoir of ice, but on multiple, disparate reservoirs simultaneously. The resulting coma becomes a site of interfering energy fronts, where the wave of water vapor and the wave of carbon dioxide gas collide, merge, and create complex patterns of density and chemistry. The hydroxyl light becomes a strobe, illuminating this interference pattern. Are we witnessing the internal seismic reverberations of the nucleus? Or could this be evidence of an external energy source interacting with the comet as a complete system, exciting all its volatiles at once? The consequence of this multi-level analysis is a fundamental shift in how we might observe these objects. Tracking hydroxyl in real time ceases to be a mere chemical assay and transforms into a new discipline, interstellar meteorology. We are no longer just measuring gas, we are forecasting the weather on a comet. We can attempt to predict the formation and movement of these hydroxyl storms, these localized gales of vaporizing ice within the coma. This is the weather of a world without a surface, a climate dictated by the interplay of deep internal stresses and the faint, yet persistent, push of stellar radiation. Can we learn to read these alien weather patterns well enough to predict the comet's next storm, and in doing so, unlock the secrets of its hidden energy dynamics? This entire investigation, from the initial ultraviolet signature to the mapping of gaseous weather systems, hinges on our interpretation of light. But light holds more secrets than just its color. Its very orientation, its polarization, can reveal the hidden architecture of the medium through which it travels. As we chart the violent, gaseous weather of the hydroxyl storms, our instruments also capture a different, more subtle anomaly in the comet's dust, a faint, opposing tail, and a peculiar twist in the light itself, suggesting that the dust, set aloft by these volatile eruptions, is behaving in ways that defy simple explanation. The appearance of an anti-tail, a spike of dust pointing defiantly toward the sun, is a rare and transient spectacle in cometary science. For most comets, this phenomenon is understood as a simple trick of geometry, a perspective effect, where Earth passes through the comet's orbital plane, viewing the larger, slower dust particles spread along the orbit edge-on, creating the illusion of a sunward-pointing spike. According to current models, this requires a specific alignment of the Earth, comet, and Sun, and is typically short-lived. The particles responsible are often considered to be large, millimeter-sized grains, resistant to radiation pressure, lingering behind the comet's main dust tail, which is blown away from the sunday. This conventional explanation provides a neat, predictable framework for such an unusual sight. Yet, when this geometry is applied to the interstellar object 3I Atlas, the model begins to strain under the weight of new data. The anti-tail observed in late 2025 persisted with an unusual intensity and structure, its morphology too defined, its polarization signatures too anomalous to be so easily dismissed as a mere line-of-sight illusion. Could it be that we are not seeing a trick of perspective, but rather the true physical architecture of its immediate environment, a structure forged under conditions we have yet to fully comprehend? This leads us to a more speculative hypothesis, that the anti-tail of 3I Atlas is not an illusion, but a tangible physical feature, a snow line sculpted by immense and unusual forces. Imagine the region around the nucleus not as a uniform cloud, but as a dynamic map of survival and destruction for volatile ice grains. Under normal solar radiation, this boundary is roughly spherical, but here, the data suggests a different reality. The coma appears stretched, pulled back toward the sun, as if by a giant, invisible hand, creating an elongated, anisotropic snowline. The finer, more volatile particles in the sunward direction are swiftly annihilated by solar radiation, while larger grains, or those protected within this strange, sunward-pointing structure, persist. This would create a visible spine of dust and ice, a river of material flowing counter to all expected dynamics, a fossil record of pressure and energy written across the vacuum. What unseen force could possibly sculpt a comet's coma into such a counterintuitive sunward-reaching form? Observational data from September 2025 provides critical context. Multiple independent analyses, both theoretical and observational, confirm the antitail's presence at a heliocentric distance of approximately 3.8 astronomical units. This is not an unusual distance for cometary activity, but the persistence and clarity of the feature were. Crucially, the anomalous light polarization data, a measure of how the comet's light is oriented, indicated that the dust grains within this antitail were of a specific size, shape, and composition that defied simple production from a typical cometary nucleus. Popular science articles from the period documented both the antitail and the strange polarization, noting that conventional dust distribution models fail to fully replicate the observations. The stage was set for a deeper inquiry. Was this the signature of a novel type of cometary behavior, or were we witnessing the external symptoms of an internal and far more potent energy source? Our analysis must therefore begin at the first level, with the simplest physical explanation. The primary hypothesis for a stable antitail involves the population of large, heavy dust grains. These particles, when released from the nucleus, feel the gravitational pull of the Sun more strongly than the outward push of radiation pressure. They thus fail to be swept into the familiar dust tail and instead lag behind, settling into a disk along the comet's orbit. When we view this disk edge-on, it appears as a sharp, sunward-pointing spike. For 3I Atlas, this would imply the object is a prodigious source of such large grains, perhaps due to a unique mineralogy or a particularly robust crust that fragments into sizable chunks. This level of explanation relies solely on known physics and requires no exotic mechanisms. It is the most conservative, and thus most scientifically palatable, interpretation. But does the mere abundance of large grains sufficiently explain the sharp, collimated structure and the specific polarization signature that was recorded? This brings us to the second level of analysis, where we introduce more dynamic shaping forces. The solar wind, a constant stream of charged particles, and the precise geometry of jet activity from the nucleus could work in concert to sculpt this large grain population. Imagine that outgassing from 3I Atlas is not isotropic, but is funneled through specific, sun-facing vents. These jets act like thrusters, but for dust. As large grains are ejected, they are given an initial velocity vector directly toward the sunday. The solar wind, with its magnetic fields and particle pressure, could then further confine and collimate this stream of material, preventing its dispersion and creating a coherent, spine-like backbone for the antitail. This model transforms the antitail from a passive debris trail into an active, dynamically maintained structure. It is a more complex picture, requiring a specific and sustained alignment of internal and external forces. But could even a finely tuned jet mechanism account for the sheer energy required to project detectable amounts of dust against the prevailing outward pressure at such a distance from the Sun? The third, and most profound, level of analysis proposes a radical, internal driver for this phenomenon: bulk phase transitions of ice. Deep within the nucleus of 3I Atlas, pockets of amorphous ice, stored since its formation in the frigid depths of interstellar space, are being warmed. As the temperature rises past a critical threshold, this ice does not melt, but undergoes a rapid, exothermic phase change directly into a crystalline structure. This transition releases significant amounts of energy and trapped gases in a sudden explosive event. Such a process could generate shock waves that fracture the nucleus's surface from within, ejecting plumes of dust and gas not just outward, but in all directions, including back along the path of the shockwave itself, potentially toward the sunday. If these phase changes occur in a cyclical, cascading manner, they could continually resupply and restructure the anti-tail on an hourly or daily basis, explaining its persistent and evolving morphology. This introduces a powerful, endogenous engine capable of generating the observed features. Is the anomalous anti-tail, then, not a product of external forces, but the direct signature of a volatile and energetic internal reorganization of the very ices that constitute this object? The consequence of this multi-level investigation is a powerful new diagnostic tool. By exploiting the unique properties of the anti-tail and its anomalous polarization, we can perform a form of remote tomography. The way light is polarized as it scatters off the dust, grains tells us about their size, shape, and density. The anti-tail morphology gives us a direct map of the distribution of these resilient, large grains. Together, they allow us to read the history of the particle population without ever touching the object itself. We can deduce the maximum temperatures these grains have endured, the radiation pressures they have withstood, and even the sequence of their ejection from the nucleus. Each anomalous data point is a pixel in a detailed image of the extreme environment surrounding 3I Atlas. This is not merely observing a comet, it is conducting a remote forensic analysis of an interstellar object. What other secrets about its origin and composition might we unlock by decoding the precise mineralogy of these sunward-pointing grains? This intricate dance of dust, light, and pressure is but one manifestation of a far more fundamental truth that is gradually coalescing from the myriad data points collected in 2025. Observations from the Swift Observatory, the James Webb Space Telescope, the European Space Agency's Trace Gas Orbiter, and countless ground-based installations are all converging, their findings locking into a single, inescapable picture. Something within 3I Atlas is releasing energy far beyond typical comet behavior. The dominant outgassing of carbon dioxide, the potential pressure cavities deep within its nucleus, the explosive phase changes of ice, and the dynamics of its jets, all these are not separate phenomena, but interconnected components of a single, powerful, endogenous activation mechanism. This is what allows it to shine with such abnormal brilliance, so far from the sun's warmth. The anti-tail is not an anomaly, it is a clue. It is the visible expression of an internal force so potent that it can sculpt the immediate space around the object, pushing back against the sun itself. And if the structure of its dust can tell us so much, what then might we learn from the state of its very atoms, from the elemental fingerprints now being teased from its brilliant, mysterious light? The chemical fingerprint of the interstellar visitor, designated 3I Atlas, presents a profound anomaly, one written not in the language of common ices, but in the subtle, metallic script of nickel and iron. The initial data from the Very Large Telescope and its UVES spectrograph in the pivotal months of July through September 2025 revealed a curious narrative. The spectral lines of neutral nickel, Ni, were starkly present, while the corresponding signature of neutral iron, Fe, remained conspicuously absent in these early stages. This is a composition that defies the standard ratios observed in the Comet of native solar system comets. According to current models, the sublimation of a comet's nucleus, driven by solar heating, should release a more homogeneous mixture of dust and volatiles, a predictable cocktail where such a stark divergence in the release timing of these two refractory metals is not anticipated. Scientists suggest this could be due to heterogeneous mineral distribution, where pockets of nickel-rich material are exposed first. But that does not account for the sheer volatility of the observed ratio, a value that fluctuated wildly as 3I Atlas plunged sunward, as if the very process of release was governed by a different, more selective set of rules. Could the conventional model of simple solar heating truly explain such a discriminatory and transient chemical signature? One speculative hypothesis ventures into the realm of exotic chemistry preserved in the deep freeze of interstellar space. Imagine not mere mineral grains, but complex organometallic compounds trapped within the ice molecules such as nickel tetracarbonyl. These microscopic laboratories, unstable when exposed to even the faintest whisper of stellar photons, would undergo rapid photodissociation. The nickel-carbonyl bonds would shatter before the more robust bonds holding iron-bearing compounds, releasing atomic nickel vapor into the coma while the iron remains locked away. An alternative, yet equally provocative, proposition is that of metallic nanoparticles, acting not as passive dust, but as active components. These minuscule fragments could function as plasmonic antennas, resonating with specific frequencies of sunlight, concentrating thermal energy on a microscopic scale, and thereby accelerating a selective, targeted decay of the surrounding ice matrix. What if the coma of 3I Atlas is not a simple plume of vaporized ice, but a complex plasma of catalyzed reactions, a chemistry set from the void? The delayed emergence of cyanogen, Cn, a molecule typically associated with the sublimation of common cometary ices, further deepens the mystery. Its late appearance, following the nickel flash, suggests an asymmetric chemical progression tied to temperature thresholds that are not uniformly distributed. This is not the behavior of a simple, homogeneous ice ball warming in the sunday. The data implies a structured, layered, or compartmentalized interior, where different materials become active at different times and under different internal conditions. The varying Nephi ratio, sensitive to solar proximity, hints at distinct release mechanisms for each metal, governed by their unique chemical traps and thermal activation energies. Are we witnessing the thermal decomposition of a structured object, one with a complex geological history written into its chemical release sequence? This leads us to the first level of analysis, the concept of spot heating. The preferential ejection of nickel before iron could be the signature of localized hot cracks. As internal stresses build within the nucleus, frictional heating along nascent fracture planes could create fleeting, intense hotspots. These zones would be just sufficiently energetic to liberate the more volatile nickel compounds or to activate the nickel-rich plasmonic nanoparticles, creating a jetting activity that is sporadic and chemically biased. It is a diagnosis of a feverish body, with temperatures rising not across its entire surface, but in isolated, flash-heated points. What internal dynamics could generate such pinpoint thermal flares deep within a solitary voyager from the stars? The second level of hypothesis proposes a more dynamic feedback process. These are not merely passive pockets of gas, but reactive jets from organometallic cavities. As these metallic organic compounds decompose, they do not just release vapor, they generate pressure. A sudden decomposition of a nickel-carbonyl pocket would not only release nickel atoms, but also a burst of carbon monoxide gas. This pressurized jet could forcefully widen the very fracture that exposed it, propagating the instability and exposing fresh, volatile material to the vacuum. It is a self-amplifying cycle where chemistry drives geology, and geology, in turn, unlocks new chemistry. Could the outgassing we observe be merely the exhaust of a chain reaction of microscopic chemical explosions rippling through the nucleus? The third, and most profound, level of interpretation considers the formation of microscopic crucibles. Within these pressurized metal-catalyzed reaction zones, temperatures and conditions could briefly reach states far exceeding what simple solar illumination could produce on a cometary surface. These are not mere hotspots, but transient, self-contained forges. In these miniature laboratories, the very microstructure of the surrounding ice and rock could be altered, with sintering, phase changes, or even short-lived catalytic reactions rapidly modifying the local composition and physical strength of the nucleus. The rapid change in the observed metal ratios would then be a direct readout of the activation and subsequent burnout of these internal microreactors. Does the interior of 3I Atlas contain a network of such fleeting, transformative ovens, constantly reshaping its internal architecture from within? The consequence of this line of inquiry is transformative for future exploration. If the Ni-Fe ratio is indeed a clue to internal thermal states, then the spectroscopy of trace metals becomes more than a chemical assay, it becomes a thermal clock. By monitoring the evolution of these metallic lines, we could potentially gauge the building internal stresses of an interstellar object. This data could provide an early warning system for imminent surface collapse or fragmentation events, a critical tool for mission planners aiming to send a probe to rendezvous with such a high-value target. The spectral lines of nickel and iron thus transition from being mere identifiers to becoming direct probes of the structural integrity of the nucleus itself. But if we can read this thermal clock, what other, more fundamental processes might its ticking reveal? This intricate dance of internal heat and chemical release, however, is set against a far more dramatic backdrop: the object's breathtaking velocity and impossible path. The very fact that 3I Atlas possesses a sharply hyperbolic orbit, completely unbound from the Sun, and travels at a staggering 210,000 kilometers per hour, forces a fundamental question. Why does an object that has never known the gravitational embrace of our star, an object that should be a pristine, deep-frozen relic, exhibit such vigorous and complex activity? For a native comet, such outbursts are the expected result of warming ices, stored from the system's birth. But for an interstellar traveler, this activity must be triggered by a different set of physics altogether. Could the immense velocity itself be the key, transforming the gentle pressure of sunlight and the impact of micrometeorites into transformative forces? The object designated 3I Atlas presents a dynamic paradox as it carves its path through the inner solar system. Its trajectory is unequivocally hyperbolic, a trajectory of escape, carrying it at a staggering velocity of 210,000 kilometers per hour. Such a path suggests a brief, fleeting encounter with the heart of our system, a gravitational slingshot maneuver around the Sun that should, by all conventional models, result in a relatively subdued display. A body on such a course typically lacks the time for the deep internal heating required for vigorous cometary activity. Yet, 3I Atlas defies this expectation, erupting in a spectacle of outgassing and dust emission that rivals, and in some aspects surpasses, the behavior of our own native, short-period comets. According to current models, a hyperbolic object, having spent eons in the deep freeze of interstellar space, should possess a volatile budget heavily depleted from its surface layers. Its activity primarily driven by the most volatile of ices, such as carbon monoxide, which can sublimate even at the vast distances where solar warmth is but a faint memory. Its activity should be a brief, superficial sputter, not a sustained, robust outburst as it approaches perihelion. But if its volatiles are so deeply buried, what catalyst could possibly unlock such energetic release under the transient conditions of a high-speed flyby? One must then consider a more speculative hypothesis. Perhaps the very nature of its interstellar origin provides the answer. Imagine a crust not forged in the familiar protoplanetary disk of our Sun, but around a distant, alien star, a crust engineered by entirely different thermodynamic and material science processes. This exogenic crust could act as a highly efficient insulating layer, a cosmic thermos, meticulously preserving its primordial volatile ices from the relentless chill of the galactic void. It would not react to solar insolation in the simple, predictable manner of local comets. Instead, its activation may require a very specific key, the unique thermal shock profile induced only by an ultra-high velocity approach. The angle of incidence, the rate of temperature change, the sheer speed itself, These factors might combine to act as a switch, a trigger mechanism that is only engaged when the object is in its high-speed flight mode. The insulation does not merely preserve. It stores energy until the precise moment the correct cosmic conditions are met, leading to a controlled yet violent release. Could it be that we are not witnessing a simple comet, but an object operating on principles of thermodynamics and material science that are, as yet, entirely foreign to our understanding? The data now arriving offers an unprecedented glimpse into this enigmatic behavior. The European Space Agency's Trace Gas Orbiter, a sentinel at Mars, captured a crucial dataset as 3I Atlas made its close flyby of the red planet on the 3rd of October, 2025. This unique vantage point, observing the object not from Earth's perspective, but from a neighboring world, provided a stereoscopic insight into its activity. Concurrently, NASA's Deep Space Network has refined its orbital parameters, confirming a perihelion passage in the final days of October 2025, at a safe distance of between 1.36 and 1.4 astronomical units, posing no threat to Earth. This precise tracking allows us to correlate its outbursts with its exact position and velocity, creating a real-time laboratory to test our hypotheses. The data stream from the TGO is not merely pictures. It is a forensic analysis of the comet's coma, its chemical composition, and the dynamics of its dust, all captured during a high-speed Martian encounter. What secrets, locked within the light spectra and particle densities, will this fortuitous observation reveal? To deconstruct this paradox, we must analyze its activity through a series of escalating interdependent physical frameworks. The first level of analysis concerns what could be termed the glide heating regime. At its immense velocity, the comet's time of flight through the region of significant solar heating is drastically compressed. The surface layers are heated rapidly, but that thermal pulse may not have sufficient time to conduct inwards to any significant depth. This creates a steep thermal gradient, a sharp boundary between a hot skin and a frigid interior. In such a scenario, the primary driver of activity may not be water ice, which requires more sustained warmth, but rather carbon dioxide ice. Carbon dioxide sublimates at a lower temperature, and its sequestration within the porous matrix of the nucleus could be more sensitive to this rapid, surface-intensive heating. The outgassing we observe could be the violent eruption of carbon dioxide, fracturing the thin, heated crust from within. But does the prevalence of carbon dioxide alone account for the sheer scale and persistence of the observed activity? Or is it merely the most visible component of a far more complex, volatile chemistry? The second level of analysis delves into the consequences of this high-speed outgassing. When gases escape from a nucleus rotating at a moderate pace, they form relatively symmetrical comas and tails, shaped by the steady pressure of the solar wind. However, at 210,000 km per hour, the mechanics of gas release are transformed. The jets of gas and dust do not merely seep out, they are ripped from the surface, achieving tremendous directional momentum. This can lead to the formation of highly anomalous tail structures, including the rare and perplexing antitail, a spike of larger dust particles that appears to point towards the Sun, an optical illusion created by the geometry of our viewpoint, and the unique ejection dynamics of the dust grains. The high speed imparts a greater initial velocity to the ejected material, creating a tail that is not just a passive streamer, but an active, collimated beam of debris. Is the strange morphology of 3I Atlas's tail not merely a visual curiosity, but a direct signature of the extreme kinematics governing its existence? This leads inexorably to the third and most profound level of analysis: thermal mechanical stress. The nucleus is not a monolithic, homogeneous body. It is a rubble pile, a collection of disparate materials held together by a weak gravitational field and its own material strength. The rapid heating during the day side of its rotation, followed by the intense cooling on its night side, creates a cyclical stress of immense magnitude. At these velocities, the thermal cycle is not a gentle undulation but a violent, hammering pulse. This induces thermal fatigue, causing microscopic cracks to form and propagate. Furthermore, the glide heating model suggests that the heat is not evenly distributed. It creates hotspots and thermal gradients across the surface. This uneven expansion and contraction can generate shear forces, leading to a phenomenon we might term thermal slip sections of the crust literally sliding against one another, opening up new fissures and venting channels. The activity of 3I Atlas, therefore, may not be a simple sublimation process, but a continuous, high-speed process of tectonic-scale destruction and renewal of its own surface. Could it be that we are witnessing the object actively deconstruct itself in real time, its outbursts, the visible symptoms of a nucleus undergoing a relentless, high-velocity thermodynamic assault? The implications of this analysis extend far beyond the academic curiosity of a single interstellar visitor. By constructing a robust model of cometary activity within this high-speed planetary flyby mode, we are essentially writing the first manual on the behavior of objects that will be the primary targets for missions. Like the European Space Agency's Comet interceptor, this mission is designed to rendezvous with a pristine comet or perhaps another interstellar object on a similar fast-inclined trajectory. Understanding the mechanisms behind the violent outgassing and dust production of 3I Atlas is paramount for mission safety. The dust and gas environment around such a hypervelocity nucleus is likely far more hazardous and structured than around a sedate short-period comet. The risks are not merely those of impact, but of encountering directed jets of high-velocity abrasive material that could compromise sensitive instruments and spacecraft surfaces. The lessons learned from 3I Atlas allow us to predict these risks, to model the density and velocity fields of the Comet, and to design flight paths that can safely navigate this most alien of environments. But if the activity is driven by internal fractures and thermal slip, can any model truly predict the sudden, catastrophic opening of a new vent? An event that could instantly transform the local environment from manageable to lethal? As we chart the volatile and unpredictable eruptions from its surface, a new and more violent question presents itself, one that concerns the very structural integrity of the nucleus. The outgassing jets are not neutral. They act as thrusters, imparting a tiny but cumulative torque on the nucleus. In a slowly rotating body, this effect is negligible. But as the rotation spins up, the centrifugal forces begin to rival the meager gravity, holding the rubble pile together. What is the critical threshold of rotational momentum that the nucleus can withstand before these internal stresses seek a catastrophic release? Could the very process of outgassing, the breath of the comet itself, be the instrument of its own eventual fragmentation? The silent ballet of a comet's rotation, a fundamental parameter dictated by the initial conditions of its formation, is not immune to alteration. As it falls sunward, crossing the frost line where frozen volatiles awaken, its very spin can be accelerated by forces unseen. The primary mechanism proposed for this spin-up is outgassing. Jets of carbon monoxide, water vapor, and other sublimated ices act not merely as streams of gas escaping into the vacuum, but as natural thrusters anchored to the comet's irregular surface. According to current models, if these jets are offset from the body's center of mass and possess a stable, non-toroidal geometry, they can apply a continuous torque. This is a straightforward application of Newton's third law, where every action has an equal and opposite reaction. The expulsion of mass in one direction imparts a rotational force in the other. Computational fluid dynamics, simulations of cometary nuclei, often predict a gradual, steady increase in rotational period under such asymmetric outgassing, a phenomenon considered a standard feature of cometary orbital evolution. The observed light curve, with its periodic brightness variation of approximately 0.3 magnitudes and a suggested rotation period of around 16.16 hours, provides a foundational dataset against which such models can be tested. This is the established, the expected, the comfortably rational. But what if the gentle push of these jets is not the end of the story, but merely the prelude to a far more violent and transformative process? Could these seemingly passive emissions be tightening a spring, winding a cosmic clock towards a moment of critical mechanical failure? The conventional view holds that outgassing torques are self-limiting. As the comet rotates faster, centrifugal forces may alter the jet structures or erode the source vents, eventually reaching a dynamic equilibrium. However, this perspective fails to account for a more insidious possibility: the positive feedback loop. Imagine a scenario where the jet itself, a conduit for superheated gas and entrained dust, begins to act as a self-lining nozzle. The intense thermal and mechanical energy at the vent throat could melt and fuse the surrounding cometary material, a mixture of water, ice, carbon dioxide, and complex organics, creating a smooth, refractory lining. This newly formed, hardened vent would then behave less like a simple fissure and more like a microscopic gas turbine nozzle. With each rotation, this nozzle channels the escaping gas more efficiently, amplifying the torque it applies. The spin increases, which in turn increases the centrifugal stress on the nucleus, potentially widening the vent and further optimizing its turbine-like properties. This speculative hypothesis suggests that the comet is not merely being pushed, but is actively engineering its own propulsion system from its very substance, a runaway process where the engine and the fuel are one and the same. Where, then, does this self-reinforcing cycle lead? Is there a point of no return, a threshold of angular momentum beyond which the fragile body cannot remain intact? The journey toward this threshold can be mapped across escalating tiers of structural compromise. At the first level, we observe a mild spin-up. This manifests as a subtle shortening of the rotational period, detectable through precise photometric campaigns. The light curve, our primary window into this distant rotation, may begin to show slight deviations from a perfect sinusoid. The jets themselves might begin to blink, their visibility modulated by the increasing speed, casting a stroboscopic signature across the electromagnetic spectrum. This is the phase of silent strain, where the internal pressures build without yet breaking the surface. The 16.16-hour period becomes a baseline from which we measure the comet's accelerating heartbeat. But if the torque continues to amplify, the nucleus must eventually respond to the immense forces tearing at its core. What internal rearrangements must occur to accommodate this ever-increasing angular velocity? This leads us to the second level of analysis, the propagation of fracture. A comet's nucleus is not a monolithic sphere of rock, but a porous, fragile aggregate, often described as a rubble pile, held together by a weak gravitational field and the sintering of its ices. As the rotational velocity climbs, the centrifugal force begins to rival the meager self-gravity, particularly at the rotational equator. Stress fractures, initiated by thermal cycling and internal gas pressure, can be pried open by this relentless spin. These fissures would not propagate randomly. They would follow the paths of least resistance, often aligning with the equatorial plane, where the tensile stress is greatest. Each new crack exposes fresh, volatile, rich subsurface material to the vacuum of space and the warmth of the sun, potentially creating new, even more powerful jets. This creates another positive feedback loop. Spin creates cracks, cracks create jets, and jets create more spin. The comet begins to actively dismantle itself, piece by piece, its rotation acting as the engine of its own destruction. The initial, simple light curve would now be superimposed with erratic flickers and flares as new volatile patches are exposed and old vents are reshaped. But can this process of systematic fragmentation be contained, or does it inevitably cascade into a terminal climax? The third and most dramatic level is that of localized fragmentation. Here, the stresses surpass the ultimate tensile strength of the nucleus material. We are no longer discussing the opening of cracks, but the actual shearing off of entire sections of the comet. A lobe, a mountain, a substantial fragment of the body could be centrifugally launched into space. The immediate consequence of such an event would be a catastrophic increase in the total surface area of volatile exposure. The pristine interior of the comet, previously insulated for billions of years, would be violently unveiled. This would trigger a massive outburst, a surge in brightness and gas production, orders of magnitude greater than typical cometary activity. The light curve would not merely flicker, it would erupt. A single fragmentation event could be followed by a cascade, as the new irregular shape of the remaining nucleus experiences altered and potentially even more destabilizing torques. The period of 16.16 hours may become a relic of the past, a memory of a more stable configuration, replaced by a chaotic, unpredictable tumble. This is the hypothesized engine behind the sudden, violent outbursts that have punctuated the lives of so many comets. But are we, from our distant vantage point, able to discern the precise moment when torque becomes trauma? The implications of this escalating sequence are profound, particularly for the future of cometary science and risk assessment. The evolving light curve, especially when combined with future radar observations that can directly measure the nucleus's shape and spin state, could become a diagnostic tool. It could allow us to read the stress levels within the nucleus, to identify the critical moment of torque that precedes a major fragmentation event. For a mission planning to rendezvous with or follow such a comet, this is not merely an academic exercise, it is a fundamental aspect of operational safety. By monitoring the photometric signatures of spin-up and the onset of non-principal axis rotation, we could potentially forecast periods of high instability, avoiding the catastrophic debris fields of a fragmenting core. The data from early observations in July 2025 provides the initial conditions for this critical monitoring. It offers a platform to test for the variations induced by asymmetric jetting as the comet approaches its perihelion. But can we learn to interpret these subtle celestial tremors well enough to predict the eruption? This very question leads us to consider the aftermath of such a critical transition. If the nucleus does cross that mechanical threshold and enters a phase of outbursts, what is the true pattern of its energy release? Is the subsequent activity a continuous, chaotic disintegration, or could it, too, be governed by a deeper, hidden rhythm? The clues may lie not in the steady state, but in the pulses. The light curve of an interstellar object is its pulse, a faint but persistent rhythm against the silent backdrop of deep space. For 3I Atlas, this rhythm has presented a profound enigma. Its activity, flaring in a series of outbursts, does not follow the chaotic, unpredictable pattern often associated with cometary bodies. Instead, it suggests a regularity, a cadence that hints at an underlying order. If this object is indeed breathing in a rhythmic pattern, each pulse of brightness could be interpreted as the signal of a pressure release valve, or perhaps a phase transition of ices deep within its core, a slow, deliberate exhalation of volatile gases. The very notion challenges our static view of comets as simple, primordial snowballs, proposing instead a dynamic world with its own internal clock. Could the fundamental nature of icy bodies be far more complex and organized than we have ever allowed ourselves to imagine? According to current models, cometary outbursts are typically attributed to the sudden exposure of fresh, volatile ice to solar radiation, or the structural collapse of overhanging cliffs, revealing pristine subsurface material. These are, by their nature, singular and stochastic events, dictated by the random geometry of erosion and the object's rotation. For 3I Atlas, One could argue that its unique composition, forged in an alien stellar system, might simply make it more prone to such discrete energetic releases. The observed slow change in coma morphology and stable baseline brightness recorded by the Falks telescopes and the commissioning data from the Rubin Observatory throughout the period from July to October 2025, prior to its perihelion, could be seen as a period of relative stability, a calm before a predictable storm of solar heating. This data provides a critical baseline, a reference against which any anomalous pulses around the 29th and 30th of October 2025 can be measured and understood within a conventional framework. However, that conventional framework does not account for the potential regularity, the suggestion of a metronome ticking within the heart of this wanderer, the Epsilon. Stable pre-perihelion data becomes not just a baseline for chaos, but a silent stage waiting for a scheduled performance. If the outbursts are not random, then what internal mechanism could possibly govern such a precise, cyclical release of energy? The anomalies defy a simple explanation of random surface phenomena, pointing toward a system that is both integrated and regulated. This leads us to a more speculative hypothesis: the existence of an endogenous pacemaker. Imagine not a single cavity, but a vast interconnected network of subterranean chambers linked by channels of nanoscale dimensions. These nanocapillaries would act not merely as pipes, but as regulated conduits, controlling the flow of superheated volatile ices from the warm interior towards the cooler crust. This entire system could function as a single, slow-beating heart, where pressure builds gradually in the deep reservoirs until a critical threshold is reached, forcing a synchronized release through these nanochannels in a pulsating, rhythmic discharge. It is a geological circulatory system, whose pulse we are only now learning to read from across the interstellar gulf. What other internal architectures, undreamt of in our solar system, might such an object possess? To decipher this cryptic rhythm, we must analyze it across escalating scales of energy and coordination. The first and most fundamental level is that of the minor pulse. This could be the signature of a single, isolated chamber, reaching its pressure limit and venting its contents into the void. A single breath from one lung of the object, a small but telling spike in the light curve that signifies a localized, contained event. It is the basic unit of this proposed metabolic process, the individual beat of the heart. But if each small pulse is a single breath, what does it mean when many breaths are drawn in unison? This brings us to the second level of analysis: resonant pulses. Here, the hypothesis deepens. It is not a cacophony of individual vents, but a symphony. The rotation of the object itself, its day-night cycle, could serve as the conductor for this symphony. Multiple internal chambers, distributed around the core, could be synchronized by the thermal tides induced by this slow spin. As the object turns, the heating from the sun triggers a wave of pressure build-up and release, not randomly, but in a coordinated sequence. The individual pulses would then merge into a larger, more powerful, resonant wave of outgassing, a harmonized chorus of venting that would manifest as a significantly brighter and more complex signature in our data. Is the rotation of an interstellar object not just a physical turning, but a timing mechanism for its internal energy cycles? The third and most catastrophic level is the outburst storm. This is no longer a rhythm, but a seizure. A chain reaction, initiated perhaps by a major structural failure or a critical temperature threshold being crossed deep within, could propagate across a wide surface area. The network of chambers and capillaries, normally a system of regulated release, becomes a conduit for cascading failure. One chamber ruptures, overpressurizing its neighbors, triggering them in a rapid domino effect that results in a massive, conflagrative eruption of dust and gas. This would be the object's fever, a violent and systemic purge that would dwarf the smaller pulses and resonant events. If such a storm were to occur, Would it represent a temporary breakdown of the internal pacemaker, or is it the ultimate, intended function of this complex system? The implications of confirming such a rhythmic pattern are profound, extending far beyond mere academic curiosity. It would grant us a powerful new tool, weather forecasting for interstellar comets. If we can decipher the pulse of 3I Atlas, if we can match its light curve to the internal pacemaker model, we could then predict its phases of activity. This would transform our approach to observing these rare visitors. Instead of staring blindly, hoping to catch a random outburst, we could choose our observational windows with precision. We could aim the most powerful spectrographs, like those on the James Webb Space Telescope, to stare at the object precisely during a predicted energetic release, capturing the chemistry of its interior as it is exposed to the vacuum of space. The ability to predict transforms the object from a mystery into a readable text. But if we can learn to predict the weather on a comet from another star, what other, deeper rhythms of the cosmos might we eventually learn to hear? This very predictability, however, hinges on the object's isolation, on the idea that its internal clock is the sole arbiter of its activity. But these objects do not travel through a perfect vacuum. They plunge through the turbulent, magnetized plasma of the solar wind. What happens when this internal rhythm meets an external, chaotic force? The next layer of the enigma presents itself not from within, but from without.